Okay, let's get started with the Chem 112 lecture series. Today we'll be discussing Chapter 5, which focuses on the stereochemistry at tetrahedral centers. So, first and foremost, let's do some review and let's talk about isomers, such as constitutional isomers, stereoisomers, and enantiomers. Constitutional isomers are structures with the same formula but a different connectivity of atoms. So in this case, if we look at these two constitutional isomers for butanol, in this case, as we can see, they have the same number of carbon and hydrogen atoms. So we have a formula of C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C4H10O. The only thing that's changed is that in one structure, the alcohol is attached at the secondary carbon. In the second constitutional isomer, we have the alcohol attached at the primary carbon. Constitutional isomers have the same formula, but a different connectivity of atoms. Stereoisomers and geometric isomers are pretty interesting. Stereoisomers are structures with the same formula, the same connectivity, but a different three-dimensional shape. An example of stereoisomers that we have seen before are cis and trans stereoisomers of substituted cyclohexanes. In this case, for this pair of stereoisomers, in one stereoisomer, both of the methyl groups are wedged, pointing up, while in the second stereoisomer, one methyl group is pointing up, while the other methyl group is pointing down. Even though these two structures have the same formula and same connectivity, as you can see from the chair conformations, these two structures have dramatically different shapes. Another example of stereoisomers would be geometric isomers, which are stereoisomers with different 3D shapes due to restricted bond rotation. A classic example of that are cis and trans substituted alkenes. Enantiomers are another class or another classification for the relationship between two compounds, where enantiomers represent a pair of molecules that are non-superimposable mirror images. Enantiomers have the opposite configuration at every stereocenter. So one example of enantiomers would be for this substituted tetrahedral carbon. As we see, these two molecules represent non-superimposable mirror images. What does that mean, non-superimposable mirror images? If we try to place these two mirror images on top of one another, they do not perfectly match. This specific mirror plane is a horizontal mirror plane. So this molecule is reflected across the horizontal axis. There are also vertical mirror planes where we reflect the molecule across the vertical axis. We'll talk more about drawing enantiomers later on. The way that we can tell these two molecules represent a pair of enantiomers is that they have the opposite configuration at each stereocenter. Here, we have the methyl group pointing up, we have the methyl group pointing up, and the alcohol pointing up. In the enantiomer, the methyl group is pointing down, and the alcohol is also pointing down. We have the opposite stereochemistry at each stereocenter if we compare a compound and its enantiomer. One easily relatable example of enantiomers would be your hands. Your hands represent a pair of non-superimposable mirror images. If you try to place your hands right on top of each other, you notice that they do not perfectly overlap. So again, enantiomers are a pair of molecules that are non-superimposable mirror images, and one way you can tell two compounds represent a pair of enantiomers is that enantiomers have the opposite configuration at every stereocenter. Let's now discuss molecular chirality and chirality centers. So a chiral molecule is a molecule that is non-superimposable with its mirror image. A chirality center is an atom, commonly a carbon atom, with 4 unique substituents. Chirality centers are also known as chiral centers, stereocenters, stereogenic centers, or asymmetric centers. For example, this carbon with 1, 2, 3, 4 unique substituents contains a chiral center. And overall, this molecule represents a chiral molecule by virtue of the fact that it is non-superimposable with its mirror image. Now, if we take a look at this pair of compounds, we can see almost immediately that these two compounds are enantiomers. They represent a pair of non-superimposable mirror images. We have a carbon center with 4 unique substituents, and so this carbon would be a chiral center. And overall, this molecule would be chiral. A chiral molecule is a molecule that contains one or more chiral centers with no axis of symmetry. And we'll talk more about axes of symmetry and planes of symmetry momentarily. Generally, if you see a carbon with 4 unique substituents, that's going to be a chiral center. And barring some exceptions, molecules containing chiral centers will be chiral molecules, with some exceptions we'll talk about. Now, how do we demonstrate that a chiral center is in fact a chiral center? Well, chiral molecules are non-superimposable with their mirror image. So you can take your molecule, which in this case, as you can see, this carbon has 4 unique substituents. This carbon is a chiral center. And then you can draw or make a model of the mirror image. As we can see, and I would encourage you to make a model for this, if we try to overlap or superimpose this molecule with its mirror image, what we see is that there is a mismatch, which tells us that these are non-superimposable mirror images. You can also see this with the model depiction of this original molecule, lactic acid, and its mirror image. It's an enantiomer. Anytime you take a molecule and its mirror image and they are non-superimposable, that tells you your original molecule is a chiral molecule. So there are 2 tests you can use. A carbon with 4 unique substituents, or another atom with 4 unique substituents, or the fact that the molecule and its mirror image are non-superimposable. These are 2 tests you can use to identify chiral molecules and identify chiral centers. To this end, let's apply what we've learned and answer the questions: is the central carbon in each structure a chiral center, and which of the following molecules are chiral? I'll do the first example, you'll do the next 2. In this case, we have a molecule with 1, 2, 3, 4 unique substituents. So this carbon would be a chiral center. And given that this molecule overall lacks an axis or plane of symmetry, we would have a chiral molecule. With this example in mind, I'd like you to pause the video and work through these next 2 problems, and then we'll discuss momentarily, with a reminder that a chiral center for a carbon center is a carbon with 4 unique substituents. Okay, so looking at this molecule here, we have 1, 2, 3, 4 unique substituents. So we have a chiral center, and given the molecule doesn't have a readily apparent axis or plane of symmetry, this would be a chiral molecule. Looking at this last case, we have only 1, 2, 3 unique substituents. We have 2 identical substituents on this carbon. So as a result, this carbon center is not a chiral center. And overall, this molecule is achiral. It's not a chiral molecule. On that note, let's talk a little bit about achiral molecules, and let's talk a little bit about axes of symmetry and planes of symmetry. So, achiral molecules, molecules that aren't chiral, are superimposable with their mirror image. Achiral molecules also have 2 or more identical substituents. So in this case, looking at this molecule here, we see we have 2 identical substituents. So we suspect that this molecule is achiral. If we take a look at the mirror image and make a model of the mirror image, if you rotate the mirror image, as you can see with this model kit, rotating this mirror image structure gives our original structure, which tells us that our molecule and its mirror image are identical. Achiral molecules are superimposable with their mirror image, and thus we have 2 ways of showing that this molecule is achiral. Another test that you can use is the plane of symmetry and axis of symmetry test. Achiral molecules have a plane of symmetry. If a molecule has a plane of symmetry, the molecule is achiral. Now, what is a plane of symmetry? It is a vertical or horizontal axis that gives identical substituents on both sides of the axis. For example, if we take a look at this molecule here, on first glance, we see we have 1, 2 identical substituents. Now, this molecule is achiral. It's not chiral. This is not a chiral center. Another way we can prove that is by drawing out and showing the plane of symmetry or axis of symmetry. In this case, if we split the molecule directly in half, directly along this vertical plane, we see that we have the exact same substituents on each side of our plane of symmetry. This is easy to say from a top-down view. So here's the drawing depiction, and here's a model depiction from this top-down view. As you can see, there's a clear plane of symmetry here, where on each side of the plane of symmetry, we have the exact same substituents. So we can see a clear plane of symmetry, and thus we conclude that this molecule is achiral. This also pops up when you talk about substituted cyclohexane and cyclopentane rings and other cyclic structures, where in this case, even though we have this bromine represented with a wedge, this is not a chiral center. This is not a chiral center. And this molecule overall is achiral. It contains a clear plane of symmetry, where on each side of the plane of symmetry, the substituents are identical. Looking at this substituted cyclopentane, again, there's a clear plane of symmetry, where on each side of the plane of symmetry, the substituents are identical. One way to think about it is that if you have the same substituents on each side of the ring, this is almost as if you had a structure that looks like this. And each of these ring substituents are identical. So we don't have 4 unique substituents on that carbon center, and thus it's not a chiral center. That's one way to think about it when you look at these ring systems. So again, achiral molecules have a plane of symmetry. If a molecule has a plane of symmetry, the molecule is achiral. Now, one of the main places where planes of symmetry come up is when we talk about meso compounds. So a plane of symmetry can be present even if the molecule contains chiral centers. A meso compound is an achiral compound that has chiral centers but contains a plane of symmetry. So for example, looking at the following molecule, we see that it does in fact contain chiral centers. There are 1, 2, 3, 4 unique substituents attached to each carbon. There are 2 chiral centers in this molecule. However, there is also a plane of symmetry. So this molecule overall is achiral. It's also called specifically a meso compound. We can prove this by taking a look at the mirror image. If you rotate the mirror image 180 degrees, you get the original molecule. So this molecule and its mirror image are identical, which tells us that this molecule, this original molecule, is achiral. It's not a chiral molecule. Now, let's take a look at another example of meso compounds. In this case, I will tell you up front that this molecule is achiral. What I would like for you to do is to identify the axis or plane of symmetry. Where is the plane of symmetry in this molecule? And I'd like you to draw it out. So take a few moments and then we'll discuss. Okay, so in this case, we have a clear plane of symmetry dividing our molecule through straight down the middle. As you can see, we have the exact same substituents on each side of the plane of symmetry. This molecule is meso and it's achiral. These are chiral centers, but the molecule overall is achiral because it contains that plane of symmetry. Let's talk a little bit now about identifying chiral centers and symmetry. A chiral center can be generally defined as an atom with 4 different groups or atoms attached. Groups are considered different if the groups cannot be superimposed if detached. For cyclic molecules, you'll want to make sure to check for planes of symmetry by numbering carbons. So for example, methyl cyclohexane contains a clear plane of symmetry right down the middle, while 2-methyl cyclohexanone does not contain a plane of symmetry, and thus this center is a chiral center. Chiral molecules also demonstrate something known as optical chirality. The compound rotates plane polarized light. Let's talk now about alkenes and alkene stereoisomers. So alkenes can have geometric stereoisomers if there are 2 unique substituents on each alkene carbon. So for example, on each carbon in the following alkene, we have 2 unique substituents. Cis alkenes or Z alkenes have the highest priority substituents on the same side. So as you can see in the Z alkene, both the chlorine groups are on the same side. By comparison, trans alkenes or E alkenes have the highest priority groups on opposite sides. As you can see, these 2 chlorines are on the opposite side of the double bond. Alkenes can have stereoisomers, but an alkene stereocenter or alkene stereocenters does not imply optical chirality. This is going to be important later on. Now, just to make sure that we're comfortable with these definitions of Z versus E alkenes, I'd like you to take a few moments and I'd like you to assign each of these alkenes as Z or E. I have taken the liberty of already assigning priority. Remember, priority is based on atomic number. The largest atomic number gets the highest priority assignment. We'll talk more about this later, but for now, I provided you the priority numbers, and I'd like you to tell me for each of these alkenes, are they Z or E alkenes? So pause the video, take a few moments, and then we'll discuss. So in this case, we have fluorine and oxygen, our highest priority groups, on the same side. So this would be a Z alkene. In the second case, fluorine and oxygen, our highest priority groups, are on the opposite side. So this would be an E alkene. Why do we use this ZE notation? Well, it's very specific, it's very exact, and it can avoid some ambiguity that we'll see in some corner case examples. It's especially useful using Z and E notation when we have multiple alkenes and when we want to name complex compounds. Okay, so we've talked a lot about chiral centers, so let's practice labeling chiral centers in each molecule. I'll do the first example. First and foremost, please add in the implied hydrogens. Anytime you have a suspected chiral center, add in the implied hydrogens. As you can see, we have 4 unique substituents on this first carbon. We have 4 unique substituents on this second carbon, and 4 unique substituents on this third carbon. This gives us 1, 2, 3 chiral centers. With this example in mind, I'd like you to pause the video and take a few moments, and I'd like you to label all chiral centers in each of the following molecules. Okay, let's discuss now. In this case, we're first going to add in the implied hydrogens. As you can see, each of these carbons have 4 unique substituents, so we have 2 chiral centers. Looking at this next molecule, this carbon has 1, 2, 3 unique substituents, so this center is not a chiral center. Let's take a look at the other carbon center to see if we'll have better luck. So here in this case, we have 1, 2, 3, 4 unique substituents. So this carbon is a chiral center. So just please make sure to always be careful and to check to see if there are actually 4 unique substituents, because it's really important to be able to identify chiral centers. Let's talk now about enantiomers, specifically drawing enantiomers. So enantiomers represent a pair of molecules that are non-superimposable mirror images. Enantiomers have the opposite configuration at every stereocenter. To draw enantiomers, we reflect our molecule across a mirror plane. There are 3 common choices. You can place your mirror next to the molecule that I call the horizontal mirror plane, beneath the molecule that I call the vertical mirror plane, and a mirror behind the molecule that can be called an inversion mirror plane. We're going to practice drawing enantiomers using this mirror plane method. So in the first case, you'll have a mirror plane behind your molecule. In this case, you're going to keep the skeleton the same and invert all the stereocenters. So if you have a dash, convert it to a wedge. If you have a wedge, convert it to a dash. Keep everything else the same. So for example, in this case, if we reflect this molecule about a mirror plane, we keep the skeleton the same. The methyl group that originally had a wedge gets a dash. The hydrogen that originally has a dash gets a wedge. Let's practice this on the following molecule. We keep the skeleton the same. The nitrogen, which has a dash, gets inverted to a wedge. The hydrogen, which had a wedge, gets a dash. The oxygen, which originally has a wedge, gets a dash. The hydrogen gets a wedge. So as you can see, we keep the skeleton the same and we invert all of our stereocenters to draw the enantiomer. The second way that you can draw an enantiomer is using a mirror plane below your molecule. In this case, you invert your molecule vertically, but you retain the same dash wedge notation. So in this case, you're essentially taking the skeleton and flipping it 180 degrees, like you're flipping a pancake. So in this case, as you can see, our original molecule, the skeleton, is pointing up, down, up. So rotating 180 degrees, and now goes down, up, down. So the carbon skeleton has been rotated vertically 180 degrees, but the dash wedge notation still stays the same. The methyl still has a wedge. It ends with a wedge. Let's practice drawing the enantiomer of this molecule using the vertical mirror plane method. So in this case, we invert the skeleton vertically. So we've inverted our skeleton. So up turns into down, up, down. Now we write out our substituents, keeping the dash wedge notation the same. So the amine keeps the dash notation. Hydrogen keeps the wedge. The alcohol keeps the wedge. Hydrogen keeps the dash. Now, I want to be clear here. Both of the enantiomers that we've drawn represent enantiomers of our original molecule. These are just different depictions of that enantiomer. Okay, so let's keep going now. Let's talk a little bit about the last method for drawing enantiomers, and I'll introduce another method for drawing enantiomers when you have only one stereocenter. So in the last method, case 3, it's when we have a mirror plane next to our molecule. In this case, you invert your molecule horizontally, you rotate your molecule 180 degrees horizontally, and you retain the same dash wedge notation. So in this case, we've inverted the carbon skeleton 180 degrees, inverted it horizontally, and we kept the dash wedge notation. The methyl group still has a wedge in both cases. Let's practice drawing the enantiomer using our original test molecule. So in this case, we have our original molecule. We take our carbon skeleton and we invert it about the mirror plane. So we invert it horizontally. We then draw out our stereocenters, keeping the dash wedge notation identical. So here we've drawn out the enantiomer for our second test molecule. Now, when you have just a single stereocenter, you can draw enantiomers using the single swap method. So enantiomers have the opposite configuration at every stereocenter. So swapping any two substituents on a chiral center inverts the configuration at a stereocenter. One easy way to see this is if we have groups labeled 1, 2, 3, 4, and we decide arbitrarily to swap groups 1 and 3, we see that the configuration changes from what we call R to S configuration. As you can see, if we count 1, 2, 3 in the first case. We're moving clockwise from 1 to 3. After the swap, if we count from 1 to 3, 1, 2, 3, we're moving counterclockwise that we call S. We'll talk more about configuration assignment later on. What I want you to recognize is that swapping any two groups inverts the configuration at a stereocenter. So we can use this to draw enantiomers. So if we have just a single carbon stereocenter, if we want to draw the enantiomer, which has the opposite configuration at that stereocenter, all we have to do is swap two substituents. For example, if we swapped the bromine and hydrogen, that in turn would give us the following enantiomer, which looks like this. By the same token, we could swap bromine and chlorine, and that would give us another enantiomer. I'd like you to try and draw one more enantiomer using this single swap method. Pick any two substituents in our original molecule and swap them. So in this case, you could pick to swap chlorine and fluorine. That in turn would give you the following. So as you can see, the single swap method is a helpful tool for drawing enantiomers if you have just one stereocenter. Let's now practice what we've learned, and then let's try to draw the enantiomer of each compound. I'll do the first two, you'll do the next two. So in this case, because I already have the stereocenters drawn out in dash wedge notation, I'm going to use the inversion method, where I keep my skeleton the same, and I invert the dash wedge notation, invert the configuration at each stereocenter. So the hydrogen, which originally had a dash, gets a wedge. The amine, which originally had a wedge, gets a dash. In this case, hydrogen originally had a dash, it gets a wedge. The methyl group, which was wedged, is now dashed. So we keep the skeleton the same, invert each of the stereocenters. For this next case, we don't have it drawn in dash wedge notation, so we're going to use the mirror plane method. Specifically in this case, just because it's slightly easier, I'm going to use the horizontal mirror plane method to draw the enantiomer. So I draw my original molecule, and now what I'm going to do is I'm going to invert the molecule horizontally 180 degrees, and I'm going to keep the dash wedge depiction of the molecule the same. If you have like a pocket mirror or a mirror in your house, you can try with a model kit or even drawing these structures and looking at your drawing or model kit in the mirror. It's a really helpful way to get used to this idea of enantiomers and used to this idea of mirror images. So in this case, we took our original molecule and we drew it across the horizontal mirror plane. So we reflected it across the horizontal mirror plane. And the reason why I chose this method is this molecule has three chiral centers, 3 stereocenters. So you have to be really careful that you're drawing the mirror image and not drawing a random other stereoisomer instead. So now with these 2 examples in mind, I'd like you to take a few moments, pause the video, and I'd like you to draw the enantiomer of these next 2 compounds. Okay, so let's now discuss. So looking at this molecule, it's drawn in Newman projection style. To make things easy, I'm going to take this molecule and I'm going to use the horizontal mirror plane method. So I'm going to reflect it across the horizontal mirror plane. And that gives the following enantiomer. So you're essentially drawing the mirror image of your molecule. Looking at this second case, it's already in dash wedge notation. So I'm going to use the inversion method. I'm going to keep the skeleton exactly the same, and I'm just going to invert my dash wedge notation. Now, you noticed I didn't draw the chlorine with a dash or a wedge. This center is not a chiral center. Your book, as well as some problems in your book, sometimes likes to label things that aren't stereocenters with dash wedge notation. So please make sure to check that a given carbon center is actually a stereocenter and not something else. Okay, so we practiced drawing enantiomers. Let's talk a little bit about enantiomers and optical activity. So optical activity is a way for us to measure a physical property unique to chiral compounds. So a polarimeter measures the rotation of plane polarized light that has passed through a solution. So we can take a light source, pass it through a polarizer, and we get plane polarized light. When plane polarized light is passed through a sample containing chiral compounds, solutions of chiral compounds will rotate plane polarized light, and in turn, we can say that these molecules are optically active. To contrast this, solutions of achiral compounds do not rotate plane polarized light. Pasteur famously noted that different crystals of tartaric acid rotate plane polarized light in opposite angles. Specific rotation of a given enantiomer and specific rotation of enantiomers are equal in magnitude but opposite in sign, where specific rotation is defined as the observed rotation divided by the path length times the concentration. So we can tell if 2 compounds represent enantiomers with one piece of evidence being that their specific rotation will be equal in magnitude but opposite in sign. We call clockwise rotation dextrorotatory, which is depicted with a positive sign, while anti-clockwise or counterclockwise rotation of plane polarized light is levorotatory, which is depicted with a negative sign. For example, if we compare these 2 tartaric acid enantiomers, one enantiomer has a specific rotation of -12, while the opposite enantiomer has a specific rotation of +12. The magnitude and sign of optical rotation is unique for each compound, and there is no simple relationship between the assigned stereochemistry and the direction of optical rotation. It really is unique on a compound by compound basis. Okay, let's talk a little bit now about enantiomeric excess and enantiomers. And let's start with the simple question of why do we want enantiomers to be pure? Well, in many cases, only one enantiomer of a compound has the desired biological activity. Why is this? Well, biological systems and receptors are chiral, and they can differentiate compounds based on their configuration and shape. Amino acids that comprise peptides and proteins are chiral. And you can think of it almost like a lock and key model, where different molecules have different binding affinities based on their configuration and shape. Only specific configurations, only specific shapes can efficiently bind to and interact with specific receptors. You can think of it almost like shaking hands, where you can tell what hand a person is using for a handshake. Now, to showcase this in terms of some compounds that we've seen in our day-to-day lives, only the S enantiomer of ibuprofen is biologically active. In another example, the S enantiomer of penicillamine can be used to treat chronic arthritis. The R enantiomer is highly toxic. So in some cases, we don't just want the desired enantiomer, we also want to avoid the undesired enantiomer. One measure of the amount of each enantiomer in a mixture of enantiomers is enantiomeric excess, known as EE, which is defined as the percentage of the desired enantiomer minus the percentage of the opposite enantiomer. You will see enantiomeric excess reported a ton in the literature when they talk about enantioselective reactions or when they talk about the separation of mixtures of enantiomers. Let's now discuss the process of assigning configuration using the Cahn-Ingold-Prelog system. So identifying the configurations of stereocenters is vital to name and differentiate compounds. To assign the configuration of a stereocenter, first and foremost, identify the 4 atoms attached to the chiral center. You're going to rank the atoms in order of decreasing atomic number, where the largest atomic number gets priority 1. So in this case, fluorine with the largest atomic number is priority 1, followed by oxygen, followed by carbon, followed by hydrogen. Looking at this next example, let's see, we have sulfur, fluorine, and oxygen and hydrogen. Sulfur is the highest priority with the largest atomic number, then fluorine, then oxygen, then hydrogen. Once we've ranked our atoms in order of priority, you're going to rotate your molecule so the lowest priority group is in the back. So in this case, if you rotate your molecule 180 degrees, we can take and move this lowest priority hydrogen to the back. Now, one quick way to do these kinds of rotations is just to swap 2 of your groups and then swap another 2 groups. So in this case, we swap the fluorine and the carbon, and then we swap the oxygen and the hydrogen. This is one way to do rotation using just pen and paper. Now, given that hydrogen is our lowest priority group here, we're going to rotate our molecule 180 degrees to place the hydrogen in the back. Using the double swap method, we're going to swap hydrogen and oxygen and swap sulfur and fluorine. You can make a model to prove that this works, and we're going to talk a lot about molecular rotation later on. Okay, now that you have the lowest priority group in the back, you're going to place the 3 remaining groups in a plane. Ignore the back group, ignore the lowest priority group for this step. You're going to draw a circle moving from the highest priority group, number 1, to the lowest priority group, number 3. A clockwise path from highest to lowest priority is designated R. A counterclockwise path from highest to lowest priority is designated S. So for example, in this molecule here, if we look and trace from the highest to lowest priority, we see that we are moving from 1 to 3 in a clockwise rotation. So this would be an R stereocenter. In contrast, if we take a look at our redrawn molecule after rotation, our hydrogen is in the back. Perfect. Next, we look from highest to lowest priority. Here, tracing from highest to lowest priority gives us a counterclockwise rotation. Which in turn means this would be an S stereocenter. Key thing, you always need to make sure and verify that the lowest priority group is in the back and your priority assignments are accurate. A clockwise rotation from highest to lowest priority is R, counterclockwise is S. Okay, let's keep going now. And let's talk about assigning configurations when we have complex groups. How do we go about breaking ties? Well, if two atoms attached to the chiral center have the same priority, you make a list of the atoms attached to each atom connected to the chiral center. You rank the atoms attached to the atom connected to the chiral center in order of priority. If a list has a higher priority group, assign the atom with that list a higher priority. So here's a classic example. We have a chiral center right here. We just have 4 carbons attached. So we still have the same atom, carbon, 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 and carbon. So we need to break this tie. So what we do is we look at the atoms attached. So in this case, attached to this carbon are 3 hydrogens. Attached to this carbon are a carbon and 2 hydrogens. Here's the carbon attached for those wondering. Attached to this carbon is a carbon and 2 hydrogens. And attached to this carbon is a carbon and 2 hydrogens. Here's the carbon attached. As we can see, we have a tie between 3 of our groups, but this group in red has 3 hydrogens attached. It is the lowest priority group because hydrogen is lower in priority than carbon. So what do we do? There's still a tie. So we have to break that tie. If there's still a tie, you look at the next set of atoms 1 bond out, and you repeat until all ties break. Okay, so we've already established this methyl group as our lowest priority group. Now, what we are going to do is we're going to move and we're going to take a look at the next carbon out. So we're going to move our dot 1 carbon down and we're going to see what we see. So we move our dot 1 carbon over and we're going to make the same list. Okay, so taking a look now, we have this carbon here is attached to a carbon and 2 hydrogens. This carbon here is attached to 1, 2, 3 hydrogens. This carbon here, looking at this blue dot, we're attached to a carbon and 2 hydrogens. So as you can see, we've broken the tie once again. Hydrogens are lower in priority than carbon, so this group is priority 3. Now we're going to keep going and we're going to move our dot one carbon out once again. We still have a tie to break. We've noted the methyl group is the lowest priority. This ethyl group is the next lowest. Now let's break a tie. As you can see, attached to the carbon in blue are 3 hydrogens. Attached to the carbon in green is a carbon and 2 hydrogens. We have a tiebreaker now as carbon is higher in priority than hydrogen. So this group on the left is priority 1. The group on the right is priority 2. Now that we have our priority assignments, we can begin to rotate our molecule in order to ensure that the lowest priority group is in the back. So in this case, what we're going to do is we're going to rotate our molecule so the methyl group is in the back. This can be done by swapping the methyl and ethyl group and swapping the left and right groups. Now that we have the methyl group in the back, we're going to trace from priority 1 to priority 3. As you can see, this is a clockwise rotation, so we have an R stereocenter. Let's do another example from scratch. So taking a look at the following molecule, we have a chiral center. Now it's important that you go one atom at a time here. So you see we have carbon, 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 and hydrogen. The hydrogen immediately is the lowest priority group. Now we're going to take a look at each of our carbon substituents and make a list of what atoms are attached. So in this case, we have 3 carbons. In blue, we have a carbon and 2 hydrogens. In green, we have a carbon and 2 hydrogens. Carbon, whoops, one moment. Here we go. As you can see, we've broken a tie in that the carbon substituent is higher priority than these other 2 hydrogens. So this group will be our highest priority substituent. Now, we have these initial tentative assignments. We have to move our dots down to break this tie. So let's do just that. Let's break that tie. So in this case, we're going to move our dot 1 carbon down. So in this case, we're now looking at the following 2 carbons, and let's list what's attached. So in this case, attached to this carbon in green, we have 2 carbons and a hydrogen. Attached to the carbon in blue, we have a carbon and 2 hydrogens. As you can see, the group in green, carbon, carbon is higher priority than carbon, hydrogen. So this group will be priority 2, and this group on the right will be priority 3. So we have our final priority assignments. Importantly, even though we have this bromine sitting at the end of the chain, it doesn't matter. We only care about the priority ranking, counting 1 carbon at a time, counting away from our chiral center until all ties are broken. Now, if we want our lowest priority group in the back, we just swap 2 and swap 2 groups. We rotate this molecule 180 degrees. That's what this swapping is doing. You can prove this with a model kit. And that gives us the following redrawn structure, which looks like this. From here now, let's include our priority assignments. Priority 1 2, 3, 4 are lowest priority groups in the back, tracing from highest to lowest priority. That in turn gives us a clockwise rotation, which would mean we have an R stereocenter once again. So, as you can see, in the event of a tie, you look at each carbon. If there's still a tie, you count one atom out, and you repeat this process. Let's talk about assigning configuration now when we have complex groups. So multiple bonded atoms are equivalent to the same number of single bonded atoms. So for example, a carbon-oxygen double bond is treated like two carbon-oxygen single bonds. A carbon-carbon double bond is treated as if there is an additional carbon attached to each of the carbons participating in the double bond. A triple bond, it's counted as if we have two additional carbons attached, and so forth. So for example, if we wanted to redraw the following molecule in a way that accurately reflects how we're going to view these complex groups for assigning configuration, this molecule, if we're looking and decomposing these complex groups, would be treated as follows. For this carbon-carbon double bond, it's treated as if we had an additional carbon bond attached to each of our double bonded carbons. And the carbon-oxygen double bond will be treated as two carbon-oxygen single bonds. Why do we care about this method of representing complex groups? Because it's very important for assigning priority. So to this end, let's practice assigning the configuration to each stereocenter based on priority. So I'll do the first example, you'll do the next two. So in this first case, looking at each of our carbons, in order to break the tie, we have to list our substituents. This carbon-carbon triple bond is treated as if each carbon had two additional carbon-carbon bonds attached. So looking at this carbon center, we see it has 1, 2, 3 carbons attached. Looking at this carbon-nitrogen double bond, it's treated as if the carbon was bonded to two nitrogen atoms. This carbon-carbon double bond would be treated as if each carbon was bonded to one additional carbon atom. So it's attached to 1, 2 carbon atoms and a hydrogen. As we can see, nitrogen is the highest priority group because it has the highest atomic number. So if we compare the substituents attached to these carbons, nitrogen wins out. So this carbon's priority 1. The carbon attached to 3 carbons is priority 2. The carbon attached to 2 carbons is priority 3. And the carbon attached to 1 carbon and 2 hydrogens is priority 4. Now that we have the priority assignments justified, tracing from highest priority to lowest priority, 1 to 3 gives us a counterclockwise rotation. So this would be an S stereocenter. To show this molecule redepicted in the expanded form, in this case, the triple bond was expanded into 2 additional carbon bonds. The carbon-nitrogen double bond was expanded into a carbon attached to 2 nitrogens, and the carbon-carbon double bond was expanded into the additional single bond each. From here we can see this carbon is attached to 3 carbons, this carbon is attached to 2 nitrogens and a hydrogen, and this carbon here is attached to 2 carbons and a hydrogen. While this carbon here is attached to a carbon and 2 hydrogens. So I'd like you to take a moment, and if needed, you can redraw your structure using the expanded notation and expand out your complex groups. And I'd like you to assign the configuration to the stereocenter in the following molecule. So pause the video, work through this example, and then we'll discuss. Okay, so first things first, I'm going to take this molecule and I'm going to expand out this carbon-oxygen double bond just to make it easier for me to start to assign configuration. In terms of atomic number, bromine is highest priority, hydrogen's lowest priority. Looking at these carbons, we have a tie. Carbon-carbon, there's a tie. Attached to this carbon are two oxygens and a hydrogen. Attached to this carbon is an oxygen and two hydrogens. Two oxygens win out over an oxygen and a hydrogen. So this group will be priority 2, while this group will be priority 3. We can now trace from highest to lowest priority. Tracing from highest to lowest priority gives us a clockwise rotation. So this would be an R stereocenter. Wonderful. So we've gotten really good at assigning configurations at each center. Let's talk now about designating configurations in IUPAC naming. In this case, the configuration of the chiral center is indicated at the beginning of the name, italicized and surrounded by parentheses. If a molecule contains multiple chiral centers, the locant number or carbon number of each chiral center is indicated before the configuration. So for example, this molecule would be R2-butanol, so this center would be R. We can prove that just really quickly. 1, 2, 3, clockwise, definitely R. Well, in this case, because there are two chiral centers, 2R is telling us carbon 2 has an R configuration, while carbon 3 has an S configuration. Let's try to name this compound. So in this case, 1, 2, 3, 4, 5. So in this case, we have a methyl group at positions 2 and 3. This is 5 carbons, so this would be pentane. So using what we've learned from all the way back in chapter 3, this would be 2,3-dimethyl pentane. But because there's a stereocenter, we have to assign that stereocenter. Looking in terms of priority, hydrogen's the lowest priority. Counting one carbon out, this is a carbon attached to 2 carbons and a hydrogen. This is a carbon attached to 3 hydrogens, and this is a carbon attached to a carbon and 2 hydrogens. We did this because we have 3 carbons and that's a tie. So to break the tie, we look at what's attached to those carbons. As we can see, the carbon attached to 2 carbons is the highest priority group. The carbon attached to 1 carbon is the next, and the carbon attached to hydrogens is the lowest. Tracing from highest to lowest priority, that gives us a counterclockwise rotation, or S. So we note this as 3s-2,3-dimethyl-pentane. If you have one of the recommended structure drawing programs, many structure drawing programs will be able to take a structure and provide a name, including configuration for that structure. So I would encourage you to, in your spare time, try and use the structure drawing programs recommended in the course Canvas shell and to try some of the naming features of those structure drawing programs, as they can be very useful tools to verify your name and configuration assignments for different compounds. So as you can see, once you assign the configuration at a stereocenter, you note the locant number, followed by the configuration, and then the rest of the name. Okay, now we've discussed a lot about molecular rotation and bond rotation. And if you have a model kit, you can just rotate your model kit until it's in the desired orientation and position. I'd like to provide you a guide to doing molecular rotation and bond rotation using pen and paper. So let's talk about molecular rotation and let's talk about some guides to molecular rotation as well as drawing stereoisomers. As we've discussed, swapping any two substituents on a chiral center inverts the configuration. For example, if I swap this bromine and hydrogen atom, even though we initially have an R stereocenter, swapping those substituents gives us an S stereocenter. So actually, the groups swapped in this case would be the chlorine and the methyl group. But you can swap any substituents and it would yield the S configuration. We can prove this because tracing from highest to lowest priority, we now have a counterclockwise rotation or an S configuration. Let's prove this with another structure. So here, this molecule has an S configuration. Just real quick as the proof for that, tracing from highest to lowest priority, this is counterclockwise, clearly S. Let's now swap two groups. You can pick any two groups to swap, and let's show that we've inverted the configuration. So I'm going to swap the bromine and the alcohol. So let's draw the molecule with the bromine and alcohol swapped. As we can see now, in terms of priority, tracing 1, 2, 3, tracing from highest to lowest priority, it's now a clockwise rotation. This center is now R. Now, obviously, if I were to take the same substituents and swap them back once again, I would get back my original molecule with the original configuration. As an extension of that idea, swapping two substituents, then swapping two substituents again on a chiral center gives the same configuration, but a different view of the molecule. So for example, if we start with an S configuration and I swap my chlorine and oxygen, we now have an R configuration. If I swap another two atoms, once again, swapping bromine and the alcohol, I now have this new view, but as we can see, tracing from highest to lowest priority, we have the same S configuration as when we started. So swapping two groups and then swapping another two groups at a stereocenter gives the same configuration, the same molecule, but a different view. This can be very, very helpful if you need to rotate your molecule into a specific view. Let's talk a little bit about bond rotation from a Newman projection perspective. So let's talk about case one for bond rotation. Any bond can be rotated 120 degrees, rotating all substituents 120 degrees. So I can take this bond and rotate it along this axis. So if I rotate all my substituents 120 degrees, just like I'm turning my steering wheel, in this case I'm making a right turn, rotating all of my substituents clockwise, we see that the bromine is now in the top position, the alcohol is on the right, the chlorine's on the left. Note, if we take a look at our configuration before and after, nothing has changed. This is still starting as an S stereocenter. It is still an S stereocenter. So we've just rotated our bonds. We've just looked at a different perspective of this molecule. We have not changed anything in a substantial way. We haven't inverted this stereocenter or done anything to our stereocenter. We're just looking at this molecule from a new perspective. This type of rotation we've actually done before with regards to Newman projections. Just to tie back to a prior skill, if we rotated our substituents 120 degrees, this yields our new view, our new Newman projection. So if you're more comfortable viewing bond rotation from the Newman perspective, you're welcome to think of it exactly like that. You're taking your bond, you're rotating your substituents 120 degrees, and then you're drawing what you see. If you need help with this, I would encourage you to make the models and rotate the models. So let's practice with this structure here. So in this case, let's rotate our substituents 120 degrees, and let's draw our new rotated structure. So in this case, let's rotate it counterclockwise just to provide a bevy of different examples. In this case, the methyl group ends up top, the alcohol ends up on the right, and the amine ends up on the left. Now, just as a check, let's just make sure that we did not invert the stereocenter. So this is an S stereocenter, and it still is an S stereocenter. So we have not changed the configuration. What we're learning here is how to rotate bonds, rotate molecules in a systematic way. This is a very important skill. And I would encourage you as you work through these examples with pen and paper to also work through them with a model kit. Because ultimately, if you make a model, you can rotate the model and get exactly what we've gotten on pen and paper. Why are we teaching this? And why am I teaching this method? Because you may not always have access to a model kit when you're taking certain standardized or other exams where you have limited materials. For my course, you will be able to use your model kit on exams, but it's important to develop both skill sets. Let's talk about bond rotation, and let's talk about what I like to call 120-degree rotations and tilts. So as we discussed for bond rotation, any bond can be rotated 120 degrees, rotating all substituents 120 degrees. You can accomplish this using the swap method by swapping two substituents, then swapping two other substituents. Your goal in this case is to place the lowest priority group in the back. Why? Because to assign configuration, you often have to rotate your molecule or redraw your molecule so the lowest priority group is in the back. So if here is our starting point and we want the hydrogen to end up in the back, we can think of it as we're rotating these bottom groups 120 degrees. What you can also think of it as a successive set of swaps where we in turn swap the hydrogen and the chlorine, and then swap the chlorine and the iodine. I prefer in this case, because we have the model view, you can think of it as if we were rotating your bottom substituents 120 degrees. So as you can see, the chlorine moves to the iodine position, the iodine moves to hydrogen's position, and the hydrogen moves to the chlorine position. And here's our rotated view. We essentially took this whole model kit, picked it up, and rotated it counterclockwise 120 degrees. Now, this is also equivalent to just taking your model and looking down the carbon-hydrogen or the lowest priority substituent bond. So we're looking down this molecule from this perspective. And as you can see, if we look at it from that perspective, we can clearly see the chlorine on the left, iodine on the right, the nitrogen up top. If we're assigning priority, we can see, tracing from highest to lowest priority, we're moving in a clockwise direction. This is an R stereocenter. So let's practice this skill, and I'd like you to tell me, what's the configuration at this stereocenter? You may have to make a model for this, or you can use the swapping method, or you can use the 120-degree method, whatever method you prefer. Okay, so let's take a look now. So we need the hydrogen in the back. So let's rotate our back substituents, these bottom substituents, 120 degrees. So the methyl group is going to take hydrogen's place, hydrogen is going to take the alcohol's place, and the alcohol is going to take the methyl group's place. This gets the hydrogen in the back. From here, we have our highest priority group being the bromine. The lowest priority group is the hydrogen. The second lowest is the methyl group. Tracing from highest to lowest priority, this in turn gives us a counterclockwise motion, which would be an S stereocenter. The other way that you can think about this is this rotation could also be accomplished by swapping the hydrogen and the alcohol and then swapping the methyl group and the alcohol. I prefer just rotating the bottom substituents because it's easier for me to visualize and it's easier for you to do with a model kit. Two methods, exact same result. Let's talk now about molecular tilting and 90-degree rotations. So if you want to tilt your carbon skeleton, what you do is you tilt the skeleton, the flat lines as needed, and you keep the dash wedge notation the same. So for example, if we want to take this carbon skeleton and we want to tilt it 90 degrees, in this case we're tilting it 90 degrees to the right, we tilt our skeleton and we keep the carbon skeleton tilted, and we keep the dash wedge depiction exactly the same. The methyl group starts with a wedge, it ends with a wedge. Note the configuration does not change, and this is a very useful check. This is an S stereocenter when we started, and it's an S stereocenter when we finished. We can continue tilting. If we wanted to take this molecule, we can tilt it further another 90 degrees, and that gives the following molecule. Tilting another 90 degrees gives us the following molecule. As we can see, in each case, we still have our S stereocenter, so we did not make a major mistake. Now, why would you need to do these tilts? Well, these tilts can be done if you need to adjust or rotate the perspective in order to place low priority substituents in the back, or if you want a particular view of the molecule, especially if you have two different drawings and you need to tell whether those two different molecules are identical, enantiomers or stereoisomers, it's often convenient to know how to redraw molecules in a specific orientation. So, to this end, let's try to assign the configuration at each stereocenter. In this case, you may need to apply a range of different methods in order to get your lowest priority group in the back. I'll do the first example and you'll do the next example. So in this case, in terms of priority, fluorine's priority 1, oxygen priority 2, carbon priority 3, hydrogen priority 4. I need my hydrogen in the back. So I'm going to use the double swap method. I'm going to swap the hydrogen and fluorine to put the hydrogen in the back. Then I'm going to swap the oxygen and the methyl group. in order to retain my configuration. So remember, in the double swap method, if you swap two substituents and then swap another two substituents, your configuration remains the same. So let's just redraw that. So the hydrogen and fluorine were swapped. The alcohol, well, in this case, the ether and the methyl group were swapped. Now let's assign and write down our priority numbers. Fluorine's priority 1, followed by oxygen and carbon. Tracing from highest to lowest priority, this gives us an R stereocenter. The other way you could have visualized it is you could also think of what you've done net is rotated this bond 120 degrees. And if you make a model and rotate the substituents on this carbon-oxygen bond, you'll be able to get the same end result. The double swap method is just particularly convenient in this case, where if you swap two substituents and swap another two substituents, you get the same molecule but drawn from a different perspective. Okay, let's now try to apply what we've learned, and I'd like you to try to assign the configuration for the molecule on the right. Okay, so approaching this example, first and foremost, we have the hydrogen as the lowest priority, carbon's the next lowest. In this case, we have nitrogen and nitrogen. So to break the tie, we look at what's attached. So this nitrogen has two hydrogens attached. This nitrogen has an oxygen and a hydrogen. This oxygen wins out, so this group is priority 1. This amine's priority 2. So we need to place the lowest priority group, which is hydrogen, in the back. So we're going to swap the hydrogen and the methyl group. We can use the double swap method. I actually am looking at this and I'm seeing a faster way. Let's just rotate our bottom substituents 120 degrees instead. So in this case, this hydroxylamine group ends up in the hydrogen's position. The methyl group ends up in hydroxylamine's position, and the hydrogen ends up in position of the methyl group. We've essentially rotated the bottom substituents 120 degrees. From here, keeping our priority assignments, tracing from highest to lowest priority, this gives us an R stereocenter. If you're uncomfortable doing these rotations using pen and paper, I would strongly recommend making a model of each of these structures and rotating the model to yield the desired view or orientation of your molecule. Let's talk about other ways to rotate your molecule. One case involves rotations and flips. So let's talk about a horizontal flip. So if you're flipping your molecule horizontally, you're going to invert your molecule horizontally and invert the dash wedge notation. So for example, in this case, if we're rotating our molecule and flipping our molecule horizontally by rotating it 180 degrees, you rotate the skeleton and you invert the dash wedge notation. This is the exact same operation as looking at your molecule from the front versus the back. So here's our front view. So the chlorine, the amine, and alcohol are in the shown positions. If we looked at the molecule from the back perspective, We see in this case, looking at the molecule from the back, we now see the hydrogens in front, the chlorine is on the right, and the amine is in the back on the left. As you can see, in rotating this molecule 180 degrees, the carbon skeleton was rotated 180 degrees, and the dash wedge on the amine and the hydrogen were inverted. In the second case, looking at a vertical flip, you'll invert your molecule vertically and invert the dash wedge notation. So for example, in this case, the carbon skeleton gets inverted vertically and the dash wedge notation is inverted. The alcohol starts with a dash, ends with a wedge. Why are these operations important? It allows us to rotate molecules to assign R and S configurations extremely quickly. So to practice this, let's assign the configuration at each stereocenter, with a hint being you'll need to redraw the molecule rotated. So looking at this case, I'll do the first example. I'm going to rotate my molecule 180 degrees horizontally. So I rotate my skeleton and I invert my dash wedge notation. So all of the dashes become wedges. From here now, we see we have hydrogens in the back, so we're good to go to continue on. Looking now in terms of priority, the carbon attached to the oxygen. So in this case, we have a carbon attached to an oxygen, a hydrogen, and a carbon. Here we have a carbon attached to a carbon and two hydrogens. And the methyl group, we just have 3 hydrogens attached. So in terms of priority, this group will be priority 1 because oxygen is the highest priority substituent attached to these carbons. The carbon attached to a carbon and 2 hydrogens is priority 2. Methyl group's priority 3. Hydrogen's priority 4. Okay, tracing from highest to lowest priority here, we're moving clockwise, so this first center is R. Let's redraw this molecule to tackle the second stereocenter. Immediately, hydrogen is the lowest priority group, oxygen's the highest. We have to break a tie. Here we have a carbon attached to 2 carbons and a hydrogen. Here we have a carbon attached to a carbon and 2 hydrogens. The group on the left wins out because carbon is higher priority than hydrogen. From here now, we can trace from highest to lowest priority. This gives us a counterclockwise rotation, so this second center would be S. So the reason why it's important to be very familiar with horizontal and vertical rotation of your molecules is that it allows you to redraw molecules very quickly to assign configurations. So I'd like you to take a moment now, pause the video, and work on assigning the configuration for this next molecule at each of its stereocenters. Okay, so let's discuss now. First and foremost, we want to make sure the lowest priority substituent, which is hydrogen in most cases, is in the back. Looking now, this first stereocenter with the amine already has the lowest priority substituent in the back. However, the second stereocenter, we need to put the hydrogen in the back, so let's draw this molecule rotated. In this case, let's do a vertical rotation. So in this case, the chlorine ends up top, the amine ends up on the bottom, and we get the hydrogen exactly where we want it in the back. We're now ready to assign priority. So Looking at this center here, the nitrogen's priority 1, the carbon attached to the chlorine's priority 2, the carbon attached to just carbons is priority 3, and the carbon attached to hydrogen's priority 4. Tracing from highest to lowest priority, 1 to 3, this gives us a clockwise rotation or an R configuration. Looking at the second stereocenter, chlorine's priority 1, the carbon attached to nitrogen's priority 2, the carbon attached to carbon's priority 3, and the carbon attached to hydrogen's priority 4. Tracing from highest to lowest priority gives us a clockwise rotation, which would be an R stereocenter. So with that, we're getting used to rotating molecules and assigning configurations. Let's now talk about assigning configurations for Newman projections and rings. So one approach, and probably the most efficient approach, is to draw a dash wedge structure for each molecule, and then from there, you can rotate your molecule so the lowest priority substituent's in the back and assign configuration from there. So let's do some practice with that. So here's our template all the way back from chapter 3. So given the following Newman projection, so in this case, we have, if we wanted to match this particular Newman projection to our template, this Newman projection matches the following template. So I'm going to draw yeah, we can use that one. There, yeah, that's the closest match. So we'll draw out our bond line depiction. From here, the upper group, which is the methyl group, is drawn flat. The group on the right, which is the bromine, ends up drawn with a wedge. The group on the left is drawn with a dash. The group in back that's pointing down, which is the chlorine in this case, is drawn flat. The group on the right is drawn with a wedge. So this is the hydrogen. The group on the left is drawn with a dash, which would be the methyl group. If you're comfortable making a model, you can make a model of the Newman projection. And in this case, the only thing that was done is that after you make the Newman projection, you just rotate the entire Newman projection 90 degrees to the right. That's all that we're doing here. So let's give you a moment to practice this. So given the following Newman projection, take a moment and let's try to draw this Newman projection in a dash wedge depiction. So in this case, this Newman projection matches this template. So we'll draw it like so. In this case, the two upper groups are drawn flat. So the methyl group and the alcohol. Looking at this carbon here, the group on the right is drawn with a wedge. The group on the left is drawn with a dash. So the iodine and methyl group get wedges, and the hydrogens get dashes. Again, all we've done is just taken the Newman projection and rotated it 90 degrees to the right. Okay, now that we have the dash wedge depiction, we're going to place the lowest priority substituent in the back and then assign configuration. So here we have the hydrogen in the back in the first stereocenter, but not the second. So one quick trick that we can do is we're going to take these substituents and we're going to rotate them 120 degrees. So we're essentially just, if you had your initial Newman projection, we're just rotating those back carbon substituents 120 degrees. This in turn gives us the chlorine with a wedge, the hydrogen with a dash, and the methyl group in drawn flat. From here, we can assign the configurations. Bromine's priority 1, this substituted carbon's priority 2, methyl's priority 3. The first center is S. The second center, chlorine's priority 1, the substituted carbon's priority 2, methyl's priority 3. Tracing counterclockwise, another S stereocenter. Given that we've already redrawn this second molecule with the following dash wedge depiction, and given that we already have the hydrogens in the back, I'd like you to take a moment and assign the configuration at each of these stereocenters. Okay, so first and foremost, at this first stereocenter, oxygen's priority 2, substituted carbon's priority 3, oxygen's priority 1, substituted carbon's priority 2, methyl's priority 3. Tracing from highest to lowest priority gives us an R stereocenter. Looking at the second stereocenter, the iodine's priority 1, substituted carbon's priority 2, methyl's priority 3. Tracing from highest to lowest priority again gives us an R stereocenter. I find for Newman projections, if you make a model and rotate the model so the hydrogens are in the back, you can often get to the correct view without as much pen and paper manipulation. Wonderful. So we know how to assign the configurations from Newman projections. Let's now talk a little bit about assigning configurations for chair conformations. In this case, you draw the chair conformation and you take the chair conformation and convert it to a dash wedge structure. If needed, you can flip the structure to place the lowest priority groups in the back. So for example, in this case, numbering 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The iodine's at priority 1, it's pointing up, so it gets a wedge. The bromine is at carbon 2, pointing down, so it gets a dash. The chlorine at position 5 is pointing down, so it also gets a dash. We can also draw this molecule out. So here's what this molecule looks like initially. As you can see, we do not have the lowest priority groups in the back in all cases. So what we're going to do is we're going to flip this molecule horizontally 180 degrees. This gives us the following flipped depiction, which I'm going to redraw with a little bit more space over here. This is why it's important to learn how to flip molecules horizontally and vertically. It saves you a lot of time. From here, we can assign priority. Iodine's priority 1, the carbon on the right. If we compare, this is a carbon attached to a carbon and a hydrogen versus a bromine and a hydrogen. So this group on the right wins out. Group on the left's priority 3. Tracing from highest to lowest priority, this is counterclockwise, so our first center is S. Looking at this bromine stereocenter, the bromine's priority 1, the substituted carbon's priority 2, the unsubstituted carbon's priority 3. tracing from highest to lowest priority. This gives us an R stereocenter. For our final stereocenter, looking at this center here, the chlorines priority 1. We have a tie initially. So let's break that tie. We count one more carbon out. This substituted carbon contains an iodine, a hydrogen, and a carbon, while this carbon just contains a carbon and 2 hydrogens. Iodine wins out. So the group up top's priority 2, and the group on the left is priority 3. Tracing from highest to lowest priority gives us a counterclockwise rotation. So this would be S. So with that, we've assigned the configuration at each stereocenter in this molecule. Let's now apply what we've learned, and I'd like you to take a look at the following molecule, and I'd like you to assign the configuration at each center. So pause the video, work through this example, and then we'll discuss. Okay, so first and foremost, let's draw this molecule in a dash wedge depiction. 1, 2, 3, 4, 5, 6. Carbon 1, the iodine's pointing up. Carbon 3, the chlorine is pointing down, so it gets a dash. Carbon 5, the alcohol is pointing up, so it gets a wedge. From here now, we see that in 2 cases, the hydrogen, the lowest priority group, is in the back, but we're going to need to draw this molecule rotated to account for the chlorine, because we need this hydrogen in the back to assign the configuration at that stereocenter. So rotating this molecule horizontally 180 degrees gives us the following depiction. Again, to rotate a molecule horizontally, you flip the skeleton 180 degrees, and then you invert every dash wedge center. From here, we're now ready to assign configuration. Looking at this stereocenter, initially, we have a tie. Counting one more carbon out, we see we have chlorine versus oxygen. We're now ready to note and assign configuration and assign priority. Iodine's priority 1, carbon attached to the chlorines priority 2, carbon attached to the oxygens priority 3, hydrogen's lowest priority. Tracing from highest to lowest priority is clockwise, so this first center is R. Looking at the oxygen stereocenter now, we see once again a tie develops. The carbon attached to the iodine is higher priority than a carbon attached to chlorine. So this gives a priority ranking where oxygen's priority 1, carbon attached to the iodine's priority 2, carbon attached to chlorine's priority 3. Tracing from highest to lowest priority gives us another R stereocenter. For the last stereocenter, in this case, we have a tie. Let's show that. To break the tie, we count one carbon out. So we have it attached to oxygen versus iodine. Iodine wins out. So now we can rank our substituents. Chlorine's priority 1, carbon attached to iodine's priority 2, carbon attached to oxygen's priority 3. Tracing, this gives you an R stereocenter. So with that, we've assigned the configuration at each atom in this molecule. So You've gotten pretty good now at this point at assigning configuration at each stereocenter. Let's now talk about one other method of depicting molecules, which is Fischer projections. So what are Fischer projections? A Fischer projection is a 2D drawing of a molecule that shows a chiral carbon at the intersection of two lines. It is a method of drawing compounds with multiple chiral centers, such as sugars. The horizontal lines, and this is very important, horizontal lines represent wedged bonds that project out of the plane of the page, while the vertical lines represent dashed bonds that project into the plane of the page. The most oxidized carbon is at the top. So for example, when the Fischer projection shows you a vertical and horizontal line, what this is telling you is that the vertical lines are dashes, while the horizontal lines represent wedges. Here's what this looks like from a model perspective. So as you can see in the model, the horizontal substituents are pointing towards us, while the vertical substituents are pointing away from us into the page. So for example, if we took the following structure and converted it to dash wedge notation, the alcohol and the hydrogen would be wedged. The horizontal substituents are wedged, while the vertical substituents are dashed. So, how do you convert Fischer projections to dash wedge structures? Well, once you've drawn out the Fischer projection in a primitive dash wedge format, what you can do is you can rotate your molecule 90 degrees to the right or 90 degrees to the left. Now, in the event that you rotate your molecule 90 degrees to the... So let's talk about this first case where we roll and rotate our molecule 90 degrees. In this case, all the groups on the right side are dashed. All groups on the left side are wedged. So what you've done in this case is if your molecule is sitting vertically like so, what you've done essentially is you've toppled it and pushed it to the right. So you've toppled it over, rolled it to the right. So every group on the left ends up with a wedge, and every group with a right ends up with a dash. By comparison, if you were to take the same substituents, the same Fischer projection, and in this case topple it to the left, all the groups on the right side are wedged and all groups on the left side are dashed. These are two different perspectives of the same molecule. So let's take a look at the following Fischer projection that's been redrawn in primitive dash wedge notation, and let's show what happens if we roll it to the right and we roll it to the left. So if we roll it to the right, our carbon skeleton in this case, we have the aldehyde followed by two carbons and then the carbon containing the bromine atom. From here, all the groups on the left end up wedged. So the alcohol and the alcohol is wedged, hydrogen on carbon 3 is wedged, while all the groups on the right get a dash. So this hydrogen would be dashed, and the alcohol on carbon 3 would be dashed. What we've essentially done when you roll your molecule to the right is you're essentially looking at this molecule from this perspective. Let's show the other roll. So if you roll the molecule to the left, your carbon chain is drawn out with the overall curve this time being curved. So taking a look at the carbon chain in the first example, the curve in this case, you can say it's like convex. While in the second case, it's more of a concave curve. So we have our aldehyde, our two substituents, and then the carbon attached to the bromine. In this case, all the groups on the right side get a wedge. So in this time, the hydrogen and the alcohol are wedged, while the alcohol on carbon 2 and the hydrogen on carbon 3 are dashed. So these are two ways to redraw and convert Fischer projections to dash wedge notation. Let's talk a little bit more about why does this work and how is this useful? Well, when assigning configurations to Fischer projections, there are two options. The first option is to view the molecule from the left and right sides and assign the configuration if the hydrogen is in the back. Oftentimes, one view will not get you will not necessarily place the hydrogen in the back in every single case. So you're going to have to get a little bit creative. And you may have to look at your molecule from both the left and right hand perspective. So in this case, let's take a look at this Fischer projection. And if you look at it from the left, as you can see, the chlorine and hydrogen. So looking at 1, 2, 3, 4, the chlorine on carbon 2 is wedged because the chlorine, as we can see in our model, is pointing towards us, as is the hydrogen. So the iodine would be dashed and the hydrogen would be wedged. Let's take a look at what happens when we view this molecule from the right. So here's the right-hand view. In this case, we see we have the iodine and the hydrogen pointing towards us, while the chlorine and hydrogen are pointing away from us. So in this case, the iodine would get a wedge and the hydrogen would get a dash. While the hydrogen on carbon 2 would get a wedge and the chlorine would get a dash. So, what can we do with this information? We now have two views of the molecule that we can use to assign priority. So let's redraw our two views. Here's our first view, and here's our second view. You can get these exact same views and perspectives with a model kit. All you have to do is look at the Fischer projection from the left and right. From here, we can now assign priority. So looking at this first stereocenter, chlorine's priority 1, carbon attached to an iodine's priority 2, carbon attached to oxygen's priority 3. Tracing, this would give us an R stereocenter. So this first stereocenter is R. Looking at the second stereocenter, iodine's priority 1, carbon attached to bromine is priority 2, carbon attached to chlorine's priority 3. Tracing, this gives us a counterclockwise or an S stereocenter. As you can see, if you look at your molecule from the left and then look at your molecule from the right, you'll be able to get at least one of those perspectives with the hydrogen in the back. Again, this is why I encourage you to use the models, because then you can make a model, look at it from the left, look at it from the right, and then draw what you see. Let's talk about a second method. I find that cyclic structures are much easier to assign configurations for, and Fischer projections are used for sugars, which exist in cyclic forms. So let's draw the Fischer projection in a cyclic form and assign the configurations from there. So in this case, for example, here's our initial Fischer projection drawn in a crude dash wedge depiction. We rotate that Fischer projection 90 degrees. And now what I'm going to do is I'm going to just pretend to connect both ends of my Fischer projection together and make a ring. They aren't actually connected, but if we draw our Fischer projection in this cyclic form, it makes it really easy to assign configuration. So in this case, as we can see here, we have a single stereocenter, the lowest priority groups in the back, ranking in terms of priority, oxygen's priority 1. This carbon is attached to an oxygen and 2 hydrogens. This carbon is attached to 3 oxygens and a hydrogen. So this top group's priority 2, the bottom group's priority 3. Tracing, this gives us counterclockwise or an S stereocenter. Fischer projections are used to describe sugars, which can exist in cyclic forms. And if you find it's easier to assign configuration when you're dealing with a cyclic structure, then draw the Fischer projection in a cyclic form and assign the configuration from there. This is a method not commonly discussed in textbooks, but I find it's a method that's really useful when you have a ton of stereocenters and you want to quickly just flip your molecule around without having to go through, make a model, and draw the different views. So to this end, let's try to apply this cyclic method to the following molecule, and I'd like you to assign the configuration at each stereocenter. So pause the video at this time, and then we'll discuss this example momentarily. Okay, so first and foremost, we're going to rotate this structure 90 degrees. This gives us the following. In this case, the alcohol on carbon 2 is still wedged. The alcohol on carbon 3 is dashed. Because when you rotate your molecule 90 degrees, essentially anything on the left gets a wedge, anything on the right gets a dash. Left, right. This alcohol is on the left, so it's wedged. This hydrogen's on the left, so it's wedged. This hydrogen's on the right, it's dashed. This alcohol is on the right, it's dashed. From here, what you can do is you can assign the configuration at the centers from here, or you can draw this in its cyclic form. Which will look like this. Now, why do we do this? Well, it can be a bit of a pain to flip and rotate this molecule when it's in the acyclic form. But from here, now that it's drawn resembling a cyclic form, what we can do is we can rotate or flip this molecule in this case, we'll flip it horizontally. And that in turn gives us the following alternative view. I find many students find it easier to flip and rotate molecules vertically and horizontally when they're drawn in a cyclic form. From here, we can assign the configuration at each stereocenter. So in this case, looking at this carbon, oxygen's priority 1. Looking at this carbon up top, it's attached to 2 oxygens and a hydrogen. This carbon's attached to an oxygen, a carbon, and a hydrogen. So this group's priority 2, this group's priority 3. Tracing, this gives us a counterclockwise. So this first center would be S. Looking at the other stereocenter shown here, oxygen's priority 1, a carbon attached to bromine's priority 2, a carbon attached to oxygen's priority 3. Tracing, this gives us a counterclockwise rotation or an S stereocenter. For those curious, the other view of the molecule that you can draw using the 2 viewpoints method would look something like this. And you can assign the configuration from there. So there are many methods to redraw Fischer projections. These are all of the methods I've found that students prefer to use and that they gravitate towards and that are pretty efficient for assigning configurations when you're given the Fischer projection. Okay, let's talk now about some shortcuts and tricks to assigning configuration. One of the shortcuts that's commonly taught is the swapping method. Swapping 2 groups inverts the configuration at a stereocenter. Thus, if we swap 2 groups to place the lowest priority group in the back, the configuration assigned will be the opposite of the actual configuration. So in other words, you swap groups to place the lowest priority group in the back. So for example, in this case, we'd swap the hydrogen and methyl group. You then assign the configuration as R or S, and the actual configuration will be the opposite configuration. So in this case, this gives us an assignment of R, but we convert our R assignment to S to account for the swap that we did. A faster trick that you can use is that if the lowest priority group is wedged, you can assign the configuration and then inverse your assignment. So let's try to apply what we've learned for this swapping method on the following example. So I'd like you to redraw this molecule, swapped so the lowest priority group is in the back, and try assigning the configuration. So in this case, I'm going to take the iodine and methyl groups and swap them. Now, I do not like this method much because you have to be really careful on this next step. So we have our redrawn structure. The lowest priority group is in the back. We rank our groups in order of priority. We trace from highest to lowest priority. This gives us a counterclockwise or S assignment. You can't forget this part. You have to swap your configuration assignment back to account for the fact that you swapped your groups. So in turn, even though our initial pseudo assignment was S, we have to swap our assignment from S to R. I find personally, if you're already swapping groups, you might as well just use the to swap method and not have to deal with this making an assignment and then swapping your assignment. But that's just my opinion. Let's talk about a quick method to draw structures. If you assigned or know the configuration at a stereocenter, you can draw the molecule in any orientation and then adjust the dash wedge so the configuration is correct. For example, if you're asked to draw 1s, for example, if you're asked to draw 1s 3s dimethylcyclopentane, you can initially draw it double wedged. And in this case, you see that this leads to assignments of R and so in this case, if you draw it double wedge, the first center will be R, the second center will be S. So from here, we only have to change the first stereocenter from a wedge to a dash, while the second stereocenter can stay wedged. So as you can see, we draw an initial draft, we assign configuration, and then we adjust the dash wedge so the configuration is correct. Let's try to apply this to 1R3S, 1-ethyl 3-methyl cyclohexane. So pause the video, take a few moments, and then let's attempt this example. Okay, so first and foremost, cyclohexane. So I'm going to draw my cyclohexane ring. We have 1-ethyl 3-methyl. So I'm going to draw an ethyl group and a methyl group. We have assignments of 1R3S. So let's take a look if it's wedge-wedge, what happens. So first and foremost, looking at this center, we have a tie initially. So let's break that tie. These carbons all look the same, so let's count one carbon out. Here we have a carbon attached to 2 carbons and a hydrogen versus a carbon attached to 3 hydrogens versus a carbon attached to a carbon and 2 hydrogens. From here, the group on the right is priority 1, the group on the left is priority 2, the group up top is priority 3. So tracing, this would give us an R stereocenter on carbon 1, so we keep it. Looking at the bottom stereocenter, let's see what we can see. First and foremost, we have another tie to break. So we look one carbon out. So here we have 3 hydrogens versus a carbon and 2 hydrogens versus a carbon and 2 hydrogens. Let's look one more carbon out to break the tie. Here we have 2 carbons and a hydrogen versus a carbon and 2 hydrogens. So we can see that the top group's priority 1, left group's priority 2, right group's priority 3. Tracing, this is counterclockwise, which would give S. So we have 1R3S. So the correct structure matching 1R3S would have wedges for the ethyl and the methyl group. Wonderful. So We have two methods to quickly draw structures and assign configuration. Let's now move on to classifying compounds. Let's talk about stereoisomers and specifically enantiomers and diastereomers. So as we discussed, enantiomers represent a pair of molecules that are non-superimposable mirror images. Enantiomers have opposite configurations at every chiral stereocenter. For example, these two molecules represent enantiomers, and as you can see, they have the exact opposite configuration at every chiral center. This second pair of molecules also represent a pair of enantiomers, and as you can see, they again have the opposite configuration at every chiral center. Diastereomers are a set of two molecules that have the same bond connectivity, but opposite configurations at one or more, but not all chiral centers. And importantly, diastereomers are not mirror images. So for example, this pair of molecules are diastereomers, given that they have the opposite configuration at one or more, but not all of these stereocenters. Now, how do we know how many stereoisomers are possible? The number of stereoisomers for a molecule is equal to 2 to the n, where n is the number of chiral centers. So for example, in this above case, we have 1, 2 chiral centers. So 2 to the n would be 2 to the second, which represents 4. So there are 4 unique stereoisomers. This represents the maximum, and there will be cases where you will have less than the maximum, and we'll talk about why. For now, let's apply what we've learned, and I'd like you to determine whether the pair of compounds are enantiomers or diastereomers. So take a few moments, work through these examples, and then we'll discuss. So first and foremost, looking in this case, we see that we have the opposite configuration at 2 of our stereocenters and the same configuration at 1. So because we have different configurations at 1 or more, but not all of our stereocenters, these represent a pair of diastereomers. They have the opposite configuration at 1 or more, but not all of the stereocenters. Let's look at this next case. Now, you got to be really careful when you have two molecules drawn in slightly different ways. And to help us see whether these two molecules are enantiomers or diastereomers, the first thing let's do is let's rotate our carbon-carbon bond so that the substituents are drawn in the exact same position. So if I rotate these substituents 120 degrees, the methyl group ends up drawn in the position of the chlorine, the hydrogen ends up in the position of the methyl group, and the chlorine ends up in the position of the hydrogen. You can also think of it as you swapped the chlorine and the hydrogen, and then you decided to swap the hydrogen and the methyl group. That's another way to think about it. Okay, so now that we have this molecule redrawn, we see that we have the same configuration at one stereocenter and the exact opposite configuration at the other stereocenter. So again, in this case, these would be diastereomers. Now, we can even go one step further and we can prove this. So this stereocenter has an R configuration. This stereocenter has an R configuration. In the second case, we have an R configuration. And at this center, 1, 2, 3, we have an S configuration. So as you can see, we have a different configuration at 1 or more, but not all of the stereocenters. So these would be diastereomers. So you can either assign the configurations or you can redraw your molecule and compare. Both methods work. Okay, so let's keep going now, and let's talk about meso compounds. A plane of symmetry can be present even if a molecule contains chiral centers, and meso compounds are achiral compounds that contain chiral centers but contain a plane of symmetry. An example of this that we discussed previously is the following diol, where we do have two chiral centers, but we have a clear plane of symmetry. As you can see, if we rotate this molecule's mirror image, the molecule and its mirror image are identical. As we saw previously, this molecule contains a plane of symmetry and would be considered a meso compound. It is achiral. This is really important because meso compounds, as they are achiral, they do not rotate plane polarized light. Further, meso compounds are identical compounds, not separate enantiomers. So these two compounds, despite looking somewhat different, are identical. You can prove this because if you take this structure and you rotate it 180 degrees, you get the following depiction, which exactly matches the structure on the left. So be really careful with meso compounds. If there's a plane of symmetry where you have the exact same substituents on each side of the plane, that's a sign that you have a meso compound, and meso compounds are achiral. So to this end, let's try to apply what we've learned, and let's draw all stereoisomers for the following compound, and let's label any meso compounds and indicate the number of unique stereoisomers. So first and foremost, in looking at this first example, we have 1, 2 chiral centers. So we'd expect 2 to the second, or 4 unique stereoisomers. So let's draw them and see what happens. So I'm going to draw one with a wedge, the other with a wedge. I'm going to draw one methyl with a dash, the other with a dash. I'm going to draw one methyl with a wedge, the other with a dash. And I'm going to draw one methyl with a wedge on the left. Let's draw that a little more nicely. Okay, so we've drawn out the 4 unique stereoisomers. However, this set of compounds are meso compounds, and these are identical. So I'm going to erase one of these depictions because they are not unique stereoisomers. They are the same compound, just drawn 2 different ways. So in total, we have 1, 2, 3 unique stereoisomers, because in the case where the configuration is the same at each of these carbons, if they're both drawn wedge or both drawn dash, this represents a meso compound. So you would not draw the meso compound's enantiomer as a unique stereoisomer. So there are only 3 unique stereoisomers for this compound, and one of the stereoisomers is a meso compound. So, applying what you've learned from this example, try drawing all stereoisomers for the following diol, and I'd like you to indicate the number of unique stereoisomers for this compound. So pause the video, work through this example, and then we'll discuss momentarily. Okay, so in this case, we have 1, 2 stereocenters, so we'd expect 4 unique stereoisomers. So we can draw both of the alcohols wedged. This should immediately set out alarm bells because this is a meso compound. I'm not going to draw both alcohols dashed because that would just be the same compound. I'm going to draw one alcohol dashed and the other alcohol wedged. And the last unique stereoisomer is the enantiomer of this compound with the opposite configuration at every stereocenter. So there are 1, 2, 3 unique diastereomers. Oh, sorry, unique stereoisomers. This pair represents enantiomers, while this pair of compounds represents a pair of diastereomers. Okay, let's talk now about identifying enantiomers and diastereomers. So let's talk about some more complicated cases and examples, and let's talk about some tricks for them. So swapping two substituents gives the opposite configuration at a stereocenter. A pair of diastereomers will have the substituents swapped at some, but not all of these stereocenters. For example, if we compare these two Fischer projections, you can see that across these two Fischer projections, the bromine and hydrogen have been swapped at the first stereocenter, giving us the opposite configuration at one of our stereocenters, but not all. So these two compounds would represent a pair of diastereoisomers or diastereomers. By the same token, in Newman projections, we see that in the back carbon, the chlorine and the methyl group have been swapped. This gives a different configuration at that back stereocenter. So one of the quick visual tests for diastereomers is to look and see if and at how many stereocenters are the substituents swapped, because swapping substituents yields the opposite configuration at that stereocenter. So these two Newman projections represent a pair of diastereomers because we've swapped our substituents at one or more, but not all of the stereocenters. As you can see by the fact that the methyl and fluorine are in the same relative position. Now, a pair of enantiomers will have the substituents swapped at all stereocenters. So as you can see, the chlorine and hydrogen on the left, all the left substituents have been swapped with all of the substituents on the right. If you look at both of the Fischer projections as well, you can see very clearly that these two structures are clear mirror images. Same for Newman projections. As we can see, the methyl and hydrogen have been swapped, and the chlorine and methyl group in the back have been swapped. If you put the structures side by side, enantiomers become really obvious for Fischer projections and Newman projections because these two structures are mirror images. So again, enantiomers have the substituents swapped at all stereocenters. So to this end, let's try to apply what we've learned, and I'd like you to identify the following as enantiomers, diastereomers, or identical. Take a few moments, and before you do these two examples, I'm going to do the first one. So first and foremost, I see that at the second carbon, the alcohol and hydrogen have been swapped. So we have a different configuration at one or more, but not all of the stereocenters. So these would be diastereomers. With that example in mind, I'd like you to try and tackle these next two problems and tell me whether these are enantiomers, diastereomers, or identical compounds. So pause the video, work through these examples, and then we'll discuss. Okay, so I see very clearly that these two structures are mirror images. We have our substituents swapped at all of our carbons. So these would be enantiomers. Likewise, looking at this pair of Newman projections, these two Newman projections and these two structures represent mirror images, non-superimposable mirror images. As you can see, we have our substituents swapped at both of our carbon centers, so all of our carbon stereocenters. So this would represent a pair of enantiomers. So you now know how to determine whether a pair of compounds are enantiomers, diastereoisomers, or identical compounds under a range of different circumstances. Now, it's important for us to take a moment and talk a little bit about, and let's take a moment and let's look at this second case in particular. There's something a little bit subtle in this second case, where even though we've seen a very clear and obvious mirror image problem, there's one other thing that we have to check for. That is planes of symmetry. You notice, in addition to the fact that these these Fischer projections look like mirror images, if we look individually, this molecule contains a clear plane of symmetry. So we have a plane of symmetry. And that tells us that even though these two molecules look like enantiomers, these are a pair of meso compounds. And as a result, as we discussed, a pair of meso compounds are not enantiomers. These would be identical compounds. You can prove this to yourself by virtue of the fact that if you take this structure and you rotate it 180 degrees, you would yield this structure. A pair of meso compounds that look like enantiomers are just two drawings of the same compound. So it's important, and the reason why I chose this example in particular is that you always need to check before doing any further analysis whether the compound you're looking at is a meso compound or not. That's very, very, very important. Okay, so now we've classified these three compounds as diastereomers, identical compounds, or enantiomers. Be on the lookout for meso compounds. Sometimes they can be hidden or not drawn in a way that makes it obvious, but if you can draw a plane of symmetry, you're dealing with a meso compound. Okay, let's now keep going. Let's talk next about prochirality. This is a concept very relevant to chemical reactions that we'll be talking about later on. A molecule that is achiral but can become chiral by a single alteration is a prochiral molecule. For example, 2-butanone is flat. It is prochiral because addition of a group yields a chiral molecule. A prochiral center is an atom that can become a chiral center by a single alteration. For example, if we replaced a hydrogen with a group X, and that would yield a chiral center, this initial carbon is a prochiral center. It can become a chiral center through an alteration or reaction. When talking about prochiral distinctions, An sp3 carbon with two groups that are the same is a prochirality center. The two identical groups are distinguished by arbitrarily assigning one hydrogen as higher priority than the other. If the center becomes R, that hydrogen is designated as higher priority. That hydrogen is pro-R. So for example, this hydrogen is a pro-R hydrogen because when this hydrogen is assigned a higher priority than the other hydrogen, 1, 2, 3, tracing gives us an R configuration. As a corollary, if the center becomes S, if the hydrogen is designated as higher priority, that hydrogen is pro-S. So if this hydrogen is designated as higher priority, the stereo center assignment is S, which means that this hydrogen is pro-S. A second prochiral distinction occurs for planar molecules. Planar faces that can become tetrahedral are different when attacked from the top or the bottom. A center at the planar face at a carbon atom is designated as the re face if three groups in priority sequence are clockwise. For example, this top face would be the re face of this carbon because looking at priority of our attached groups, the groups are clockwise. The psi face occurs if approach from that face would yield the groups counterclockwise. I always like to assign the re face first. The psi face is the opposite face. Okay. To close out this chapter, I'd like to discuss some unique examples of chiral compounds. So the first case are chiral compounds that don't have chiral centers. These are known as atropisomers. An atropisomer is a stereocenter resulting from a hindered carbon-carbon or other bond rotation. A classic example are BINAP and other related ligands, where these molecules, despite not having a tetrahedral center, these molecules overall are chiral because rotation across this carbon-carbon bond is constrained. So you can have S and R binap based on the relative 3D arrangement of your aryl group substituents across this carbon-carbon bond. The second case of a chiral compound without a chiral center are allenes. Due to cross-conjugated pi bonds, the allene substituents are perpendicular to one another. So for example, this methyl group and hydrogen are held perpendicular to this secondary methyl group and hydrogen. Because the two pi bonds are cross-conjugated with one another. You can think of it almost like you have a vertical plate for one of your substituents and a horizontal plate for your other substituents. So these two allene stereoisomers would be enantiomers, and you can prove this by making a model. So allenes are one example of chiral compounds without chiral centers. The substituents on the leftmost carbon and the substituents on the rightmost carbon are perpendicular to one another. The two substituents are exactly perpendicular, and as a result, depending on the relative arrangement and position of substituents, these two molecules, even though they look very similar, have different three-dimensional shapes and represent non-superimposable mirror images. The last example of chirality and unique examples of chirality are at nitrogen and phosphorus. Nitrogen is not particularly useful as it readily inverts at room temperature, so nitrogen does not form a chiral center that is useful, and individual enantiomers can't be isolated. For phosphorus, because it inverts more slowly, chirality at phosphorus can be observed and enantiomers can be isolated. The lone pair is the lowest priority group for RS configuration assignment. So nitrogen inverts readily, phosphorus inverts slowly. So phosphorus, this phosphorus atom, represents a chiral center that is stable, and you can isolate specific diastereoisomers and enantiomers of phosphorus containing compounds with phosphorus chiral centers. On that note, let's talk about separating enantiomers. Now, because enantiomers have identical physical properties, they cannot be easily separated. However, diastereoisomers have different physical properties and can be separated via physical separations. So, although we can't separate enantiomers using physical methods directly, what we can do is we can use a chiral resolving agent to convert our enantiomer into a set of diastereomeric salts. This gives diastereomers that are separated by their differing solubility or polarity. So for example, if you have a mixture of enantiomers, you react it with a chiral reagent, and this makes a set of diastereomers, and these diastereomeric salts can be separated. Now, if you don't want to do that, there is another method to separate enantiomers, and that is chiral column chromatography. A chiral column contains chiral molecules as part of the stationary phase column coating. As enantiomers will have different interactions with the chiral column, the enantiomers will progress through the column at different rates and exit the column at different reaction times. Thus, a mixture of enantiomers can be separated. So, in chiral column chromatography, you have a column and it's coated with a stationary phase. The trick in this case is that the stationary phase is coated with chiral molecules. And as such, if you have, for example, an R and S enantiomer, they will progress through the column at different rates because they interact with your stationary phase and your chiral stationary phase to different degrees based on whether they're one enantiomer or the other. So this allows us, because these two enantiomers progress through the column at different rates, we can collect and separate our enantiomers as they leave this chiral column. So these are the common methods used to separate enantiomers: chiral resolution or chiral column chromatography. The last thing I'd like to talk about, which is going to be a lead-in for our future chapters, is alkene stereochemistry and assigning Z and E configurations. So in cases where there are multiple substituents on an alkene, we utilize the IUPAC convention of Z and E assignment. To do this, you rank each group on each side of the alkene separately in order of priority. If the highest priority groups are on the same side, you have the Z configuration. If the highest priority groups are on the opposite side, you have the E configuration. For example, in this case, on the left, fluorine is higher priority than carbon. On the right, oxygen is higher priority than hydrogen. Since fluorine and oxygen are on the same side of the alkene, this would be the Z alkene. Conversely, in this case, since fluorine and oxygen are on the opposite side, this would be the E alkene. Let's try to practice this now, and I'd like you to assign the configuration of the following alkenes. I'll do the first two, you'll do the next two. So in this case, first and foremost, the group with the carbon with the oxygen attached is higher priority than a carbon with carbons attached. Here we have a tie. To break the tie, we look here. Remember, a double bond is treated as if we have an additional carbon-carbon bond. So looking at this carbon, we have 2 carbons and a hydrogen attached. At this carbon, we have a carbon and 2 hydrogens attached. The group on the bottom is higher priority than the group up top. As we can see, the 2 highest priority groups are on opposite sides, so this would be the E alkene. Looking at this next example, this group is higher priority than hydrogen. Looking here, a carbon attached to a carbon and 2 hydrogens is lower priority than a group attached to a carbon and 2 hydrogens. As you can see, the 2 highest priority groups are on the opposite side, so this would be another E alkene. With this example in mind, I'd like you to take a few moments and try to assign the following alkenes as either E or Z alkenes, respectively. Pause the video, take a few moments, and then we'll discuss. Okay, so first and foremost, the methyl group is higher priority than hydrogen. Chlorine is higher priority than carbon. The highest priority groups are on the same side, so this is a Z alkene. By the same token, chlorine is higher priority than methyl, and a carbon attached to an oxygen and a hydrogen is higher priority than a carbon attached to a carbon, and a hydrogen. Oxygen is the higher priority group. This gives us priority 1, 2. Since our highest priority groups are on the same side, this is also a Z alkene. We will be talking about alkenes and alkene reactions a lot in future chapters, so it's important to be familiar with EZ notation. Okay, so that concludes our discussion of Chapter 5. We'll be moving on to Chapter 6 as part of the next lecture series.